Okay. And how about I share my screen? And even better, you guys know how every week I'm like, oh my God, one of these days I'll finally learn how to use Photoshop. I did it. Okay. So watch this. Oh yeah. Isn't that way better? So much better. Look at this. Okay. Hopefully, wait, you could see this, right?
Yeah.
Oh yeah. Okay. I did it. And then look at this. Oh my God, I can even get an eraser. And oh wait, I have to do it this way, but one of these ways I can get an eraser. All right, I guess not. Good enough. Okay. Yeah, somebody actually asked the stereochemistry question, which I think would be worth looking at because I was trying to like look at it really fast right before we started, and then, well, I didn't make it. Okay, and then I gotta. Oh well, I still have to flip back here sometimes. Okay. All right, maybe there's a learning curve here. One of these days I'll make it. Okay, cool. Yeah, why don't we even just start with this and warm up because, well, we'll probably do some stereochemistry today anyway. So let's talk about it. Okay, so the question is kind of to like rank the or to write whether this is an R or S stereocenter, right? So which of the two that it is. And well, I was looking at it pretty fast, and you could see it's marked up by the excellent person who sent this to us. Yeah, well, I mean, we can go through, okay, hydrogen is 4. We know that. That's easy, right? And then everything else is carbons. Well, that's kind of annoying. So let's go to the next one. Right. So here we went 1, 1, and 1. Okay, those are all carbons. So let's move to the next ones. Okay, here we have 2 carbons. Here we have a carbon and an oxygen. And here we have an oxygen, right? Not counting the hydrogens. All the hydrogens are kind of not very relevant. Okay. So we would expect this to be our highest priority group, and then this to be our second, and then this to be our third, right? And so we have 1, 2, 3, and we have a hydrogen or number 4 in the front, right? So this goes this way. So in this case, the car is going to the right, but this guy's in the front, not in the back, right? So we get that this is S. Not a great answer because the textbook says it's R. So, yeah. Well, I got S when looking at this, so I don't know if anybody else is seeing something that I missed. It's totally possible. In fact, maybe even likely. But when I looked at this I saw that it was S. I don't know.
Isn't the like left also CCO? Because there's like a carbon at 2, 1, and then the oxygen. I don't know, but then that'll be the same weighting as the other one.
You mean this one that I've ranked as 1?
Yeah, maybe. Yeah.
So if we look at this carbon, it has this carbon over here and an oxygen here, right? And this guy over here has just the oxygen.
Yeah. Okay.
That's what I was trying to say. Yeah. Yeah. So it looks like this should be S, which is weird. Maybe the textbook has a typo. That would be surprising, but possible. Yeah. Unless anyone sees some things I'm missing, because it's totally possible. But yeah, when I was looking at this, it was S. So, okay, cool. Anyway, yeah, that was a good question. And let me erase it now, so that we can actually start the notes or the what we normally do. Oh wait, I'm in red. Hang on. Oh, what is my? Oh, I have to change a setting. I bet. Let me change my setting. It's worth it, I promise. Applied. Okay. Oh yeah, there we go. Now I can do this. Okay, that'll be nice. So why don't I switch to the black pen? Okay, I already had it. Okay, cool. Anyway, again, learning curve. Okay, cool. So this week we talked about alkynes. Right? And I mean, these aren't new to us. We've seen them before. So they just look like a triple bond. They're nice and straight molecules, right? Like the triple bond makes them like 180 degrees the whole way down, right? And then we could draw other stuff and, you know, whatever, right? All this extra stuff doesn't make a difference. Well, it can make a difference, and the time that it does is when we have an alkyne with 2 carbons on either side, or if we have an alkyne with a hydrogen, right? And so here we know that this is called an internal alkyne, and this is a terminal, right? And well, we haven't said that much about internal alkynes because we can't make them yet, or we haven't really been able to make them. Although terminal alkynes we kind of already have dealt with, right? The exact reason being that we could take these things and add something that's a really strong base, right? And we can deprotonate. And okay. Here we go. We could deprotonate these things, right? And then this is a pretty good nucleophile. In fact, you get bonus points if it's just this guy, because this is like a really great nucleophile, right? This thing is tiny, and it's got a minus charge on it, and you have to give it a pretty good base to be able to do this. So that's pretty nice. All right, I really thought I had it. I might have to switch back to this in disappointment and shame. Because it won't let me get my eraser out. Okay. Yeah, so the reason we can do this is because this terminal alkyne has a pretty low pKa. Does anybody remember what the pKa of this thing is, roughly speaking?
Like 25.
Exactly. Yeah. So this thing has a pKa of around 25, so it's pretty good, right? And then what are some bases we could use to do this?
Like Na, NH2, NH, and then like any C minus, or like a C carbon with a negative charge.
Yeah. Yeah. So this sodium amide is mostly what I was thinking, because this is like the common one that's like easy to make. Yeah, if you have something that has like a carbon with a minus charge, you could probably do this too, but it's less likely that you'll have a carbon with a minus charge. Yeah, I guess this is probably the best one, but you could imagine a situation where there's some carbon with a minus charge that could do it too. Yeah, there are some other bases that could do this too. LDA comes to mind, which is also a nitrogen that has a minus charge, but well, you don't have to be creative. Again, there's no points for being creative, so sodium amide will work perfectly fine. Okay. And yeah, and then once we have this, well, we could do one or two things, right? So there's the old route, which is that we could do SN2, okay? And so this is just to displace, right? Because it's a good nucleophile, okay? We've seen it. The other thing that we could do, and this one is new for us, is that we can give it a ketone or an aldehyde, either of the two, right? And the idea is that this oxygen is really electronegative. And in general, when you have a carbon and an oxygen together, this is already a pretty polar bond, right? Because this oxygen is like kind of minus, and this carbon is kind of plus. But I mean, it's not that big of a deal when you just have a single bond. But once you have a double bond, you get like sort of twice the effect. Like not really. It's certainly a lot more complicated than that. But you can kind of think about it that way, right? This is like extra plus and extra minus. And so the idea is that this carbon is like a really good electrophile, okay? And it's not often that we talk about electrophiles, but like the idea is that a nucleophile will really love to go here and then push these electrons up, okay? And so, I really thought I had it, okay. Yeah, and so, like without this, all this extra stuff, whatever, we just get rid of it like this. Okay. So without all this extra stuff, well, these electrons can go up here, kick them up to the oxygen, and so we wind up with an O minus here. Okay. And from there, we just give it some light acid, okay? Some like, you know, fairly weak acid. It could be something really like not concentrated. It really doesn't have to be. And okay, cool. Look at this. We get a tertiary alcohol now. Okay. And if we really want, we can get rid of these triple bonds. Okay. So this is a pretty nice thing that we can do. And in fact, I might even go so far as to say that like most of the remaining reactions that you'll learn in this class and in organic chemistry 2 are going to be of this style, where you have something that's a pretty good nucleophile and is attaching onto a carbonyl, and you're getting a like an alcohol up here or something in that style, right? So just as another example, just to show you what's coming, and in fact, something that might even be like a sort of question that they might ask. They could ask sometime in the near future, right? Is if you were to have a compound like this, which is called an acid chloride, and let's say you were to give it this guy, acetylide, right? Well, what's going to happen is it's going to come up here and kick the electrons to that oxygen, right? So we have this chlorine, and then we have our triple bond. Okay. Well, this chlorine's a pretty good leaving group, right? And that carbonyl is generally really stable. So what can happen is we'll kick off that chlorine and recover our ketone now with a triple bond on it. Okay. So this is a possibility. There's a whole bunch of other very similar reactions because, you know, there are ketones, there are aldehydes, there are these acid chlorides, there's a whole bunch of things. But this is the style, the flavor of things that you're going to see a lot more of, well, in the next week or two, when there are more lectures about like this sort of carbonyl addition stuff. And then like half of organic chemistry 2 is dedicated to these reactions. So you'll see plenty of them. And well, you'll already have seen them in organic chemistry 1, so it'll be pretty nice going through organic chemistry 2 and seeing a lot of the same reactions showing up again. Okay, so this is something that's to come.
Quick question.
Mm-hmm.
I actually watched the organometallics lecture, and can you get the same ketone product using the organometallics, I guess?
Yes, you can.
Okay.
So what you're referencing is like when you what will come is that you can actually get rid of carbons you can have carbons with minus charge. Oh, so I guess that's what you were referencing with the alkyne thing earlier. Yeah, good point. It's uncommon that you do that. At least I haven't. It doesn't show up as often because normally you're just trying to deprotonate the alkyne, and it'll be more work to make the organometallic and then deprotonate. Anyway,
right.
But yeah, you're totally right. And so these organometallics refer to things like, you can have something that's like this with a lithium, which for all intents and purposes is this thing, and then with the lithium, right? Or alternatively, there are other options. So you can also have this guy, this MgBr, and this is called a Grignard reagent. And there's also another one, which is, I don't know if you talked about this one, but you can also have something that looks like this with a copper in here. These are called organocuprates. But these guys react differently, so we'll put them off to the side for a moment. Yeah, so if we have either of these two, they could do the same thing, right? So first off, they could take this terminal alkyne and they could deprotonate it, right? So this is a really common reagent. So this is butyl lithium. Okay, and so this can deprotonate it just fine because this is a super basic carbon, right? So that would look like this. Okay. You could do the same thing with Grignard reagents. They're also pretty similar. They, for the most part, they just react the same as these organolithium compounds. So you could treat them as being the same. But anyway, yeah. So if you looking ahead, if you want to do reactions with these organometallics, well, you can give it butyl lithium here, for example, right? It's going to kick off, well, I guess I should say, it'll come up here, right? Move these electrons up. We get an O minus, a chlorine, and then a butyl group. Kick that down, kick the chlorine off. You get a new ketone. And in fact, this is the main way of extending carbon chains, okay? As far as I can think about it, there are 3 ways that you learn over both semesters of organic chemistry to extend carbon chains. So there are 3 ways, yeah, to extend carbon chains. Okay, and one of them would be to use one of these guys. Another would be organometallics, which is coming soon. And then the third one, well, it shows up at the end of next semester. So that's a long time to go from here. So so this one comes much later. There's some really specific name for them. It's like, I can't even really remember the name. There's some whole class of reactions that comes much later, and you'll see them, but for now, I wouldn't worry about them. Okay.
Do you know if organometallics are on this quiz?
They're not.
Okay.
Wait, I thought they were.
Oh, they were?
Yeah.
Okay.
Yeah, they are.
Yeah.
Okay. All right. Follow that. Okay. So, oh yeah, sorry, you're right. They're in chapter 10 and chapter 10 is on the quiz, right? I'm thinking about this week. Yes, you're totally right. Thank you for correcting me. I would have suffered if I wound up telling you the totally wrong information. Okay, thank you. Yes, yeah, they are. They're part of chapter 10. All right. Yeah, it's actually worth mentioning from like some perspective, what you will learn by the end of this quiz, or really by the end of this semester, right? Which there's only like 3 weeks left of, woohoo. that kind of makes up the majority of the reactions that you'll see in organic chemistry in both semesters. The second semester, a lot of the reactions get recycled, like a lot of them. I mean, they'll throw like, 20, 25 reactions at you per chapter and say like, oh yeah, you should just know all of these, right? But what will come in real handy is that a lot of them are just specific cases or straight up repeats of what you've seen before. So there will be whole chapters about like, there will be a whole chapter, I think, on like acid chlorides, for example, right? And we just talked about basically the main use of acid chlorides. Like this is pretty much it, right? I don't know how they write a whole chapter about it, but they do. So the idea is that like, well, you'll see these things again. And it's really valuable and important to get a good handle on them now. Which is not to say that you won't be able to pick up on all of it again next semester. But get it. Organic chemistry 1 is really about like the general classes of reactions, like broadly. And then in 2, you just kind of like pump out reactions. So. Yep. Okay. Anyway, where was I? So, okay, cool. So we have these alkynes, right? We could do SN2. We can add them to carbonyls. That's new and very important, right? And okay, you can do like, it doesn't just have to be these carbonyls that we're adding them to. Okay, we can add them to acid chlorides. We can add them to ketones, to aldehydes, whatever else there is. You can't add them. Actually, it's worth mentioning. You can't add them to these guys. Why not?
Would it just deprotonate the carboxylic acid proton?
Exactly. Right. All that would happen here is this. And then we're back to the start. That kind of sucks, right? We kind of just lost a lot of progress there, right? No reason to do that. So yeah, point being, there's a whole bunch of these things, right? I mean, I wrote like a few down, right? So ketones, aldehydes, acids, acid chlorides, but there's others, which I can't really think of right now. And I think there's like 2 or 3 more. Anyway, they all do their own things. They kind of react differently a little. They react special. So you'll get to see those down the line. But for now, things like this are sort of things that you've seen before, right? This is a pretty good basis. Well, we know it's a good acid because it's literally in the name, right? So you do an acid-base reaction, stuff like that. Okay. Anyway, there's only a few more reactions, at least as far as I remember or saw in the lecture, that alkynes that are really special to alkynes. Okay. So I said earlier that we can have something with an alkyne, right? And then whatever, okay, we can give it whatever else on the sides. And we can get rid of this alkyne if we wanted, right? And that's a perfectly good way of extending a carbon-carbon chain. In fact, you could just skip some stuff with organometallics, and you could just use alkynes and then hydrogenate at the end if you really wanted, right? So if I want to just turn this into a single bond, what can I use? Up here.
Oh, you can add like H2 and platinum or palladium, and it's like a catalyst.
Yeah, exactly. Right. This is exactly the same as alkenes. Okay. Again, you don't have to be creative. You could use just totally the same thing, right? So platinum is fine. You could also use palladium or nickel were the other ones that you could use. So yeah, you could do that. But, well, that's not really great because we just spent all this time last week talking about so many reactions that you could do with alkenes, right? So these alkynes are fine, but we can't use them to make an alcohol, for example, or we can't use them to selectively put on a bromine at one spot, or whatever other host of all the other reactions that we just talked about. So it would be very nice, and in fact it is, and for this reason there are reactions to do it, if we can go from here, and well, there are two different kinds of double bonds that we can make, right? So we can make this trans double bond, or we can make a cis double bond. Okay, and that'll be able to give us different stereochemistry in our final product, which we want, right? There will certainly be some questions where they ask like about getting certain stereochemistries at the end after using an alkyne. And well, you're probably going to have to use one of these two. All right, well, so how do we do it? So for making a trans double bond, what do we use?
Wouldn't it be NaNH3?
Yeah, exactly. So NaNH3, and then usually when we write this, this is ammonia, and ammonia is like normally a gas at room temperature. So you got to have it really cold. And anyway, so we write it as a liquid because this happens in liquid ammonia. Okay. And down here, cis double bond.
Can you do the H2 with palladium, but with Lindlar's catalyst?
Yeah. So this is with Lindlar's catalyst. And anybody remember what Lindlar's catalyst is? So I think you said palladium, but what else does it have?
With the some kind of impurity, like a Na something. Was it?
Okay.
Was it barium sulfate?
Yeah, exactly. Yes. So it is an impurity. You're exactly right. It's barium sulfate. Okay. And that makes it so that you get a single addition, right? There's something about how like when you have this barium sulfate on there, it's just easy to get. It's easy. It's energetically favorable enough, I guess. So it's easy enough to just add one hydrogen on there, but adding the second hydrogen is harder, right? It's not as like favorable, so it doesn't happen. And so anyway, this works really well. You don't have to write palladium and barium sulfate every time. In my experience, they just take it if you write Lindlar's. So you don't really need to remember this. You could just write Lindlar's catalyst. And in my experience, that's been totally fine. So take that as.
Isn't there this substance with like the two rings and then the nitrogen?
Oh, yeah, you're totally right. Yeah, how could I forget? And so there's also quinoline or quinoline or however you pronounce it. Again, you got to be able to write it. You don't have to be able to pronounce it. Yeah, so it is this thing. And this structure has like two rings. Yeah, two rings on it. This is what actually competes with the hydrogen. Yeah. Yeah, you were totally right. So.
And that's all covered under Lindlar's, right?
Mm-hmm. Yes. Yeah. Yeah, so if you write Lindlar's catalyst, you should be good to go. Right. That's nice. Okay. And well, anyway, this Lindlar's catalyst thing, this is a hard reaction to write a mechanism for. I know in lecture he writes some stuff about how like, oh, there's this wall here, right? And then you like, I don't know, sit down hydrogen on it or something, whatever. In general, when there's like a metal catalyst involved in a reaction, we don't really write the mechanism because there's some surface stuff that's happening there, and that's really complicated, right? Like you could do a PhD on it. So we're not worried about it for this class. But this one up here, we can write the mechanism for, and in fact, you should know the mechanism for it. So how about we do that? Okay, here we go. Let's write this. Okay, and well, all right, well, what happens? What happens when we put this sodium in the ammonia I should start with?
It forms like a free electrons.
Yeah, exactly. So there's just all these electrons that are floating around. Okay. And they see this alkyne, so what do?
They attack the triple bond.
Yeah, exactly. Okay. So one of them will attack, right? And then, okay, here we go. We've already got our double bond. Now it's got a minus on that side and a radical on the other side, right? Okay. And we know, well, we know in the end that we have to pull a hydrogen from somewhere. So where do we actually take that hydrogen from?
NH3.
Yeah, exactly. It's the only thing around that has hydrogens. Okay. Cool. And so that gives us a hydrogen up here, right? We still have our radical down here and all the extra stuff. Okay. So what happens again?
An electron attacks, and then you have like a lone pair.
Yeah, exactly. So I guess I should be writing single arrows or single-headed arrows because we write those whenever only one electron moves, right? So, okay, yeah, we get a lone pair, exactly, right? Get a lone pair down here. And all this extra stuff. Okay, and well, it's just gonna pull another hydrogen. Okay, cool. And there we go, we got it. Okay. So this is the mechanism for making this trans double bond, right? This one's good to know. Again, I still think it's pretty unlikely that they would ask for you to like write down this mechanism just because it's so like, you know, well, people could just look it up, right? And I think their strategy is to avoid that. So I think it's probably unlikely that they would ask for one of these, but well, they could. And it's one that in usual times, you're certainly expected to know. So I could see them asking about it. It's definitely fair game. Okay. Good. And yeah, so that's how to make cis or trans double bonds. Well, and then there's just a few more, right? So, well, why don't I ask you guys? So what other reactions are there with alkynes? I can think of 3 more, kind of 2, but.
Like the oxymercuration, demercuration, and the hydroboration, oxidation, and then I think the kappa reaction.
Exactly. So oxymercuration, demercuration. Let me even. I ran out of room. Okay. Okay. Well, we'll keep those other 2 in the back of our mind, but while we're here, right? Let's look at a terminal alkyne because that just makes things more interesting. And I'll just start writing R, right? So if we want to do oxymercuration, demercuration, Well, we'll just use one of these bonds, right? We don't want to use both of them. So what are we going to use up here? We know that we'll use sodium acetate, or sorry, mercury acetate, right? And what else do we normally have?
H2SO4.
Yeah, exactly.
Professor Molander wrote it as HGSO4, but like it doesn't really matter because everything's like solvated, right?
Yeah, so I forgot about, normally we write HGSO4. In the past, I've looked this up and like the reasons on it aren't like super clear. A lot of the time people just write on like people have asked online and the answer is usually just like, oh, you just use HGSO4 because like, I don't know, that's just like the standard.
Like he
Yeah,
wrote
so-
HG with like the acetylide, and then he wrote HGSO4 on the bottom. But like he also used X as like the counter ion for all the reactions. So I think he like is like OAC and SO4 kind of interchangeable.
So as far as I remember, yes. This is probably the sort of thing to check me on or look up. Yeah, I've seen this as HGSO4 when working with alkynes, but I don't remember it being especially important.
Okay.
So you're right. Yeah. But it is typically written this way. I guess to be on the safe side, maybe this is one case where like it might not be best to be lazy and just write HGSO4 because that's the standard thing that people use in this case. Yeah, although I think I personally expect that it would be unlikely that they would like get on your case if you used sodium or mercury acetate, but whatever. Yeah, so we use this, and then this is a multi-step, right? Actually, I think in this case it's not, right? In the first case it is, but if I remember correctly, this time it's not. Although, maybe correct me if I'm wrong. Anyway, what do we get once we do this reaction? What is our product? Given that it's kind of weird, right?
A methyl ketone.
Yeah, exactly. Okay. So we wind up getting a methyl ketone, and maybe I will just write it. Maybe I'll write this a little bit to the right, because the way that might be easier to think about it, right? Because getting to this product is like, okay, how did we actually get there? So you could think about it as doing the Markovnikov alcohol addition, right? And then from here to the final product, you do what is called the keto-enol tautomerization. Oh no, my roommate's alarm is going off. Hang on. Sorry, that thing is aggressively loud. So, yeah, got to deal with that. Okay, so anyway, this keto-enol tautomerization is like important. Okay, it's a bit hard for me to, I don't know, overstress the importance of the keto-enol tautomerization. You'll see it a whole bunch, like a lot. Okay, so this is a case where we might as well look at it in depth. So why don't I make a new thing? Okay, and let's actually look at what this thing does. So let me go full screen because that's way nicer. So here's this keto-enol tautomerization. Okay, so the idea is that we have this guy here, which is called an enol, and then we want to get it there really is an equilibrium, but it's like really, really in that direction. Okay. And then we're getting it to be ketone. Okay. And so this can happen under acidic or basic conditions. So let's say it's acidic. All right. What happens is we start with our enol. And remember, acidic means we only ever have plus or neutral charges, which is to say no minus charges. No minus charges allowed. Okay. So what does that mean? Well, let's draw the electrons that we have to work with, right? And you could write this in like one step or two steps, but how about we write it in as many steps as we can, right? So we have a bunch of acid floating around. You could assume that water is there. And so these electrons are going to come up and grab that hydrogen. Okay. So this is an equilibrium again, right? And well, we lost the bond here, so it's a plus charge. And okay, we got that hydrogen. That's good. Right? So these electrons will come down. Okay. So now we've moved the plus charge up to here. This is way more stable, again, remember, because it has an octet. Everything has the full octet. Right? And okay, now getting from here to this final ketone, well, that's not bad, right? We could just take water, pluck off that hydrogen, and there we go. Okay. So this is a mechanism you totally need, you like 100% need to know. Absolutely, like super important. This is a key mechanism. And I say that a lot. Although you might be thinking like, okay, it shows up in these two stupid reactions, right? Oxymercuration and then demercuration, and then hydroboration, right? Like, okay, it's two things, right? Like whatever, it's not going to show up very much more. Earlier I was saying how half of organic chemistry is about like adding things to ketones. The other half of organic chemistry too is about this keto-enol tautomerization, okay? In some vague sense, right? This will be key. Again, you will see this thing like forever. This thing will haunt you in your nightmares. It will always be there. So while it doesn't show up in huge amounts this semester, you 100% you will need to know it. Okay. Anyway, cool. So the point is, it can happen in both acidic and basic conditions. So this is what happens when it's acidic, but how about we write out what happens when it's basic? Okay. And with basic, you can imagine the difference is that no plus charges are allowed. Okay. So here we go. Let's start with what we have. Okay, and well, we can assume that there's just a bunch of this hydroxide floating around. Okay, so let's just follow our nose. What's this hydroxide going to do? Anybody?
Grab the hydrogen.
Yeah, okay. There's a real symphony there of pull off the hydrogen or deprotonate. Okay, so exactly, that's what it can do. And so here we go. We have an O minus and this double bond. Okay, so what is this O minus going to do?
Negative charge is going to move down. and then the double bond is going to shift to the carbon.
Yeah, exactly. Right. There we go. Okay, we have our ketone. We have a minus charge over here. We're almost there, right? Last step, we have to get that hydrogen on there. So let's pull it off of a water. And we're done. Okay. So let's look at that again. Okay, so we pulled off the hydrogen, right? We made an O minus. That's pretty easy to do. We kicked that minus charge down, so we got our ketone, and then we got a hydrogen off. Okay. So, yeah. Compared to with acid, well, we protonated first, then we made the ketone, and then we took off that hydrogen. Okay. So they kind of go backwards to one another, but well, yeah, they kind of do. In like, well, I guess there's kind of two ways of going about this. So for one thing, you could just like, well, memorize it, right? Like you could just remember what happens, and it's only 3 steps for each of them, so it shouldn't be that bad. But you could also like not memorize it and sort of just figure it out each time. I don't think I've ever really like sat down and memorized exactly how they go. It's just kind of like, I know that at one point you have to give the double bond to some hydrogen, right? And you have to do some protonation stuff with this carbon, with this alcohol, or deprotonate. Right.
Hey Adam, could you briefly go through the mechanism from turning the alkyne into the enol?
Yeah. Right. So the mechanism. The mechanism for this oxymercuration, it looks similar to the one when there's just a double bond. And my details on this might be a little bit rusty, but bear with me. So if we have this HGSO4, right, the triple bond is gonna come here and take this thing off. Although, well, you don't even really need to take the SO4 off. I think you really just have like Hg2 plus floating around, which will do this, but whatever. Yeah, so it'll look something like this, right? Yeah, let's see. Then you'll have a water, right? Which will come in here. It'll attack the more substituted carbon because, well, that's the more positive one, right? That's where the positive charge would like to sit more. This positive charge up here. Yeah, so what do we have? Okay, so there's a water sitting on here. Right, this mercury is now, should be neutral, I think. And so we have this. Okay, and well, we could deprotonate, that's not bad. And so we have our mercury and our hydrogen left on here. Okay. And anybody want to fill in the rest? How do we get rid of this mercury?
Would it be like SO4 in solution?
Yeah. So there is Yeah. So this is particular where my memory like gets pretty bad here. Yeah. So let me actually try to find exactly what happens, because I don't remember exactly the detail, but so okay, yeah. Oh, so, okay. So this does have a plus charge, by the way. Yeah, it's fine. Whatever. Yeah. Okay. Anyway, that's this should have a 2+ charge. That's fine. Yeah. So what is the point? Okay. So there's what happens is this double bond goes to a hydrogen because there's a bunch of, right, we have sulfuric acid, so there's a bunch of hydrogens floating around. You could pull it off of water too, it makes no difference. Okay, and so we get this. Okay, so we wind up going down to the single bond. Okay, and then from there we just drop the mercury. Okay, and that's our enol. I drew it upside down, but well, it's the enol. Yeah. Yeah, that is a good question. Sorry about that. Yeah, I haven't written out this reaction in a while, and I guess it is different because, well, in the other case we have to, like, let's see, we have to reduce the mercury off, right, using sodium borohydride, but in this case we don't, because we have an extra bond that we can move around with, right? We have a double bond here that we can play with too. So, well, this was a plus charge. Yeah. So that gives us enough freedom to get rid of that mercury on its own. No sodium borohydride needed.
Thank you.
Yeah. Yeah, that was a good question, and reminded me of the mechanism too. So, yeah. Thank you. Cool. Okay. Anyway, so this is it, and this is what we can use to make so we can use this to make internal, well, ketones, or just, I should just say, in general, we use this to make ketones. Okay. And if we want to make aldehydes, you already know what we're doing. We're gonna do hydroboration. And in this one, yeah, we still have to do the oxidation. That step is still necessary. Okay, so if we have our terminal alkyne, right, we can do the same thing as normal. The catch is that we don't want to use something that has multiple, we don't want to use a thing with boron that has multiple hydrogens, okay? Because, well, it'll just hydroborate multiple times. That's a problem. So we need something that only has one hydrogen, okay? So we need a BH and then something, okay? So what are people's favorite something here?
Saya.
Yeah. So Saya 2. So if we want to say this out, this is diisocyanamyl boron, boride, or whatever. I don't know, whatever it comes after it, but this is diisocyanamyl is the point. Yeah, so that's one option. There's a couple others. Anybody remember any others? I think of one that was mentioned in class, but, well, there are more that are common outside of class.
I think Professor Molander used like a cyclohexane attached, like two of them attached to a BH.
Yeah. So there are a few other options, right? So cyclohexyl is one, where, so this is another one. There's also this other thing called thexyl borohydride, whatever this suffix is. Thexyl is another one, which almost looks exactly like isocyamyl, but it's like slightly a tiny bit different. There's also another one that's called 9-BBN, which that one I know he mentioned in class, which was like it's like this. Well, without drawing it in huge detail, it looks like this. There's this huge ring. Okay, and so this ring is like a big parachute kind of for this boron, right? Anyway, not super important. The point is that like these are some options that you could use, or that you might see. Thexyl, you might not see. I think I've seen it once in organic too, maybe. I know that when I've looked things up online, I've seen it often. Like it's a common one to see online, so that's why I mentioned it. But yeah. Okay. Anyway, so we give it this BH2. Again, no points for being creative. This is the one that I remember too, but there are other ones, so take your pick. So we go ahead, we add that, right? It does a syn addition. Right, and then, well, whatever else was attached to it. Okay. And from there, there's a whole bunch of extra steps, but we just do the second part of the reaction where we add, in this case, hydrogen peroxide. We add a base, right? This is what does the oxidation. Okay, cool. And so we get an alcohol. Oh, I totally added it on the wrong side, didn't I? Yeah, I did. Sorry about that. Yeah, that boron is going to want to add on the less substituted side, right?
So I briefly brought this up on Piazza, but there was a textbook question where like they were equally substituted, but like both R groups were linear chains. So this reaction made like a mixture. Yeah. So I was just like wondering, how do you know like how substituted something is, or like how bulky an R group is when they're substituted equally?
Yeah, you're right. I mean, if things are pretty equally substituted, right? If we're talking like primary, secondary, tertiary, if they are both like, let's say secondary, you're gonna get a mixture of the two. There are a few cases where like that's not the case. So let's say we have, for example, let's say we use like will be a good case, right? So if we have this, for example, right, and then something that looks like this, something that's really huge, right? These are both secondary substituted, but this thing is going to get much more in the way.
Right.
So
if it was like a methyl and like a really long linear chain, like that would still be a mixture, right?
Yeah, it would still be a mixture. It would like, if you had like this thing, it would still favor, right? If we use one of these things that has like a super bulky group, right, it would still favor this thing.
Right.
It would favor this over the other one. But yeah, I think it still would be a mixture. I haven't seen very much that they've asked a question where like you're using the bulkiness of the actual thing to get one of two equally favorable sites. Yeah. In general, I think they'll probably be asking about, if we had like this, right, then it's the answer is clear, right? It would just be this one and not any of this. Yeah, I think in that case it would work fine. I haven't seen them ask something like that before. I know he mentioned it during lecture, so it is fair game, right? But I think it would be fair to say it's a mixture anyway, and then maybe say like, oh, this is the major and this is like the minor product or something, right? If we don't have this thing. But yeah, I wouldn't expect it too much. Or you'll be using this in synthesis anyway, and when you're doing synthesis, right, it's all fair game because you can do whatever you want. So so then it's totally up to you. But yeah, the point is, yes, you get mixtures in a case like that. So yeah, it can be messy. I should also mention there is a nice case where, for example, let's say that you have, I don't know, whatever, we'll make it look like this, right? Something like this where it's symmetric. Well, in that case, it doesn't make a difference, right? Right, and then, okay, so step 1, we do that. Step 2, we give it stuff to oxidize, okay? And well, if it adds onto here or here, it doesn't matter because we can just flip the molecule around. So a nice case is when, and I wrote this as a double bond, but actually, why don't I even just go ahead and do it as a triple bond? In this case, it doesn't make a difference because we will just get this. Okay. So this is a nice case that you can get to. But otherwise, it's a mixture that's determined by steric stuff. So that would be it. Yeah. Okay. Let me go ahead and erase. Oop. Okay. Anyway, back up to here. Yeah, so we go and we fill the rest of this in, right? And there's an OH. Okay. And then we tautomerize. I guess I should, oh yeah, equilibrium arrows is fine. Okay. We tautomerize, right? This is a basic tautomerization. Not that it makes a difference for our product, but for the mechanism, it sure does. So we wind up getting the aldehyde. Okay. So that's pretty nice. We have a way of making aldehydes too now. Okay, anyway, last reaction. So this is the zipper reaction. And well, I know I was watching the lecture because, well, when I took the class, they didn't actually even cover this reaction. But, well, it was talked about in the lecture, but it didn't seem like he talked much about the mechanism or anything. He kind of just seemed to say like, oh yeah, it's the same sort of mechanism as when you're making an alkyne into a trans double bond, which is that you load an electron on and then you reduce, you give it a hydrogen, and then you load an electron on and you give it a hydrogen. You kind of just keep doing that over and over until your alkyne winds up at the end. So anyway, not too much for me to say about this one because, well, I haven't really worked with it that much before. And it seems like the sort of reaction that just kind of works. So we take this, right? What is the reagent that we use? Someone mentioned it earlier. What do we use here?
Like kappa?
Yeah, exactly. So it's kappa. So if I remember correctly from the lecture, that's just, we use this potassium hydride and then this guy. Okay. But you could just write kappa, no problem.
So when we're doing like a synthesis, we can just write this out if we're trying to create the terminal alkene.
Yeah, I guess so. Apparently, yeah. That's what it seemed like from the lecture, and he drew out a pretty complicated molecule, right? I drew it moving one step over, but from what I remember, the one that he wrote out was like a whole, like the alkyne was like seriously in the middle of the carbon chain, and then it just moved all the way to the end. So yeah, you could just use it to move it to the end. My guess is that the terminal alkyne is the most stable of these somehow, at least under these reaction conditions they might be. So it like where you can move the alkyne wherever, but it's going to land up on the end because that's the most favorable. At least that's my guess. But it wasn't covered that much, so I wouldn't expect that that's the sort of thing that they'll like really drill you on. It seems more of just like a really useful tool for doing like synthesis reactions. So yeah, maybe something to look out for. Again, have not worked with this reaction very much, but something that I could see them tricking you on is that this potassium hydride, this will react with alcohols, right? It will react with minus charges. It'll react pretty aggressively. So if you have a bunch of extra stuff in your molecule, you better be sure it's deprotonated at the end of whatever you do, right? If there's a lot of excess kappa, then yes, you could still do this, but you better deprotonate your alcohols. So you will actually, I totally missed this myself. I always do this, right? Where I'm like, oh, you got to look out for this, and then I do it myself. This should be a minus charge here. Because it's in something that's super basic, right? There's a hydride there. It's going to pull off that hydrogen. So yeah, be sure to watch out for that one because I just demonstrated you can miss it pretty easily. Okay. Cool. How are we feeling? Okay. Ready to do some problems? Use the, wait. Oh, wait, this is always my favorite thing to use. Use the buttons in the participant panel. Like press like yes if you're feeling okay. Oh yeah. Nice. We got some yeses. My favorite thing to do. I feel like these like little Zoom icon things are super like underused. They're really fun. Yeah, and actually, why don't I should send this thing too. So there's like a sign-in sheet, kind of like usual. So anyway, fill out that sign-in sheet. You don't have to do it now. I'll send it again at the end, but do fill that out. It's good for you. No, it doesn't make a difference for you, but you know, do fill it out at some point. I'll send it again at the end. Okay, anyway. Okay, cool. Let's do some problems. Anyway, we've been talking a whole bunch. Let's do some of these. All right. Here we go. So the question is, so how would we do synthesis? Well, let me save this thing and oops. Nope, I don't want to save that. Here we go. Okay, cool. And why don't I even just make a new thing? Okay. And let me start copy and pasting. The question is, we want to start with compounds that have no more than 6 carbons, and we want to, do these synthesis problems. So why don't I move this problem up to here, and then zoom in. Oh man. Okay. Here we go. So no more than 6 carbons, and we want to, let's say, synthesize this. And this problem tells you, for example, like this is something that you might do, right? This is like an example of what that problem is. So here we have 1, 2, 3, 4, 5 carbons, right? And then we are giving it this guy, right? And this is just SN2. This is a primary iodide. Like It's fantastic, right? It'll come off like butter, no problem. So SN2, and we can make something like this, right? So now the question is, how can we make something that looks like this? And well, let's start off with the obvious. So we want to count carbons, see how many we've got. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's kind of a pain in the ass, right? We got 9 carbons, so we're gonna have to actually have to work for this one, right? So why don't we go backwards, right? This is the point where we have enough reactions now at this point in the course that we can really like, well, it's not going to be really like obvious for any of these how we should go from the start to the finish, especially when they don't give us what we're starting with. So we might want to work backwards on this. Okay. So I'm going to draw our favorite retrosynthetic analysis arrow. Okay. And well, what do we notice about this final molecule that we know how to do?
Like a syn dihydroxylation.
Yeah, exactly. Right. So, whoops. Okay, this thing is really big. Here we go. That's ugly. It's okay. Whoops. I drew one carbon too few, right? There we go. If we have a double bond there, specifically a cis double bond, well, we can go from here and syn dihydroxylate. And what do we use to do that?
Like catalytic osmium tetroxide and hydrogen peroxide, I think.
Exactly. What is the other option?
Cold dilute permanganate.
Yeah. So the other option is cold dilute potassium permanganate. Okay. I'll skip writing that out. Yeah. Okay, so that's the syn dihydroxylation. Okay, cool. Now we're working with something, right? We have to be able to get this compound. Okay. Well, we know that we're going to have to make or break a carbon-carbon bond anyway, and we only have one way of doing that so far, right? Well, I guess by the quiz you'll have another, but that'll involve having carbonyls, and that's a lot more work. So the point is, how are we going to get this double bond in the first place, right? And how are we going to get all those extra carbons on there, right? So where did this double bond have to come from?
Could it come from an alkyne that was hydrogenated with Linder's catalyst?
Exactly. Yes. Yeah. So that's what I was trying to get at. Maybe in way too many words and not enough clarity. Yeah. So we want to do a syn hydrogenation here, right? Except we want a double bond out at the end so we can write Lindlar's catalyst. Okay. No need to be more fancy than that. Okay. And now this is nice, right? Because look at this. This is an alkyne, and it's attached to a carbon that's just sticking out, right? So how do we get this alkyne on there? Let me draw it down this way.
Like an SN2 reaction.
Perfect. Yes. Right. So we can say cut this bond here. Oops. So we can cut this bond, and that will get us 2 compounds. So here we go. We can pick whatever one we want here, right? So let's just put iodine because, well, it'll work perfectly. It's excellent for SN2. And then we also want we want this alkyne here. Okay, and so this happens by SN2. Okay, and lastly, well, we have to make this alkyne somehow, so how do we do it? We can start with this guy here, and what can we add? Oh, whoops. What do we add here?
Like butyl lithium.
Yeah, sure. Butyl lithium, perfectly fine. Okay. And so that's what we had to do. If we want to be like elegant about it, which, well, I guess we should, right? If we were writing this out as an answer, you should, like, this is the thought process you should take, but then at the end you should write out from scratch, right? So then what we might say is, okay, let's start with this compound. We can add butyl lithium, an excellent choice, right? We will get the anion. Okay, we can add our SN2 reagent here. Okay, and then once we're there, we get this guy with a triple bond on it. Okay, H2 Lindlar. That gives us our cis double bond. Okay, and from there, syn dihydroxylate it till we're done. So H2O2, then catalytic osmium tetroxide, and okay, we're done. We made it. Yeah. Okay. And just to preempt the inevitable, right? We also get these guys going back. Okay. But the question was just to get, well, while the question drew them as wedges up here, right? There's not going to be, like, there's no good way to do this with getting them, like, getting this specific stereochemistry, right? At least certainly not in this class. So we'll get both of them. The question is just to get both of them on the same side, right? So we got what we wanted. All right, let's keep at it. Copy, paste. Okay. Oh, and now I just have to do this. I wonder if there's a keyboard shortcut. Oh, yeah, there is. All right, let me get even more advanced. What was it? Control T, I think.
Before,
oh, yeah.
for the like if you had them both wedges or both dashes, aren't they kind of the same because you can rotate around your single ones?
So they won't be, and the reason is just because, whoops. Oh, man. The reason is because both of these are chiral centers. And so here, I don't know, these are like R and R or something. I don't know exactly what they are. Whereas these over here are probably like S and S, right? And rotating or moving around in space isn't going to change either of those two. And so we're kind of stuck with with those. Those R and S is like fixed. We can't change those. So. Yep. The unavoidable, inescapable presence of stereochemistry. Okay, here we go. So we have next one. Let's start off again. See if we can cheat this problem by just starting with something with 6 carbons. Well, we can't. This structure has more than 8 carbons. We can only start with 6. So we got to do some work. Okay, but there's an aldehyde here, and we only have one way of making aldehydes so far. You will have more later, but for now there's just one. Right? And so what is that method?
Hydroboration oxidation.
Yeah, exactly. Right? So let's say we start with this structure here, right? With an H on here. So what we could do is step 1, you can add diisocyanamyl borohydride. It's not borohydride, it's something else, but whatever. Okay, well, that's actually all you need to add in step 1. And then step 2, right, we add sodium hydroxide, H2O2. And that makes us an aldehyde, right? I mean, you have to do a keto-enol tautomerization in there somewhere. Don't you dare forget about that. But you don't have to write it out. It just happens automatically, right? There's such a high preference for the keto form, the ketone. Well, I guess in this case, the aldehyde, but same difference. There's such a strong preference that the enol form is pretty much irrelevant. Like it doesn't really, there's like 1% enol, but that's just inevitable. Whenever you have a ketone or a carbonyl, really, if you can have an enol next to it or at that position, you'll have like 1% or a small amount, like a tiny fraction. But point is, we don't worry about it that much. At least not in syntheses. Okay, anyway, so here we go. We have this, right? And well, at this point, we can probably even go ahead and break this bond, right? So how do we make the structure here?
SN2.
Yeah, exactly. Yeah. Both of you got it. So SN2, I don't know. We're going to pick iodide again. No need to be creative, right? And then this acetylide ion. Okay. And so this happens by SN2. Okay. And I have the feeling I don't need to tell you how to make this acetylide ion. So, yep. This one's nice. This one was 2 steps, right? The last one was actually a bit more, but this one, no. Okay. Nice. Let's get the next one going. Copy and paste. And look at this. Watch this. Oh yeah, I can even do it with keyboard shortcuts. Now I'm getting really good. Okay. Sorry, you guys have to listen to me learn how to use Photoshop. Okay, here we go. So what are we working with here? Well, we have this alcohol and we have this little aldehyde hanging off the side here, and they're opposite to one another. So maybe I'll even, if we're thinking about this big picture, and if somebody is really good at looking at this and they're you know, you're really picking up on the patterns. We have an alcohol and it's opposite to something else. It's it's trans to something else. In this case, it's trans because it's on the ring. How did we probably get that?
With an epoxide opening.
Yeah, exactly. Okay. So we will use an epoxide. Okay. They love epoxides. You'll get asked about epoxides plenty of times. So, yep. Okay. Anyway, we can't use an epoxide as our first step, right? Because we can't just stick that aldehyde onto there. It doesn't work, right? Like, we cannot just do we can't just, add this because this doesn't really exist, right? Like, this is not like really a thing. This is not going to work. So we might as well just get rid of it. But, well, okay. So we'll have to make this aldehyde after we already open the epoxide. Okay. So how do we make the aldehyde? Again, only one way.
Hydroboration oxidation.
Yeah. Yep. Oh, whoops. Well, so we actually have a triple bond here, right? Okay. So 1 diisocyanyl borane. I think that might be what it's called. Whatever. Okay. And then again, hydrogen peroxide, sodium hydroxide. Okay. Ingrain those reagents into your brain. I mean, you will use them over and over and over again. So, plus it can be really easy to forget them, right? There's like a whole bunch of reactions here. So just wait. Actually, I think in the next chapter, there's this reaction called the Swern oxidation, which has like 1 million reagents, like so many. Not really, it has like 4, but like, oh my God, what a pain. Anyway, that's coming in the next week. We'll talk about it on Thursday. By the way, we do have a workshop on Thursday, remember? So, yeah. Anyway, someone just unmuted. If you were going to ask a question, it's totally okay.
SN2.
Oh, yeah. Okay. Yeah, anyway. So for this problem, yeah. Yeah, we can open this epoxide. Right. Like this. Right. And well, there's a slight subtlety here. It's like super small, but this thing will actually, it won't give us this. It'll give us the deprotonated version of it. Right. So we will actually get this O- and a triple bond here. So there's like that slight subtlety of this oxygen, which we'll have to deal with. But, well, why don't we not worry about it right now? We get the gist, right? And then, well, this thing, we've already seen how to make it, right? Just hit it with some sodium amide or butyllithium or your organometallic of choice, for example. Okay, so how about we write this out? So we're gonna want to make this epoxide. Technically, we don't even have to because this thing has 5 carbons, but just for good measure, let's do it, right? So let's start with this thing over here. Okay, what do we add to make an epoxide?
MCPBA.
Yeah, exactly, right? PBA. Yeah, give it MCPBA and don't even think about it. Right? And so we'll wind up with this thing, right? I'm justified in writing these bonds as wedges because, well, this compound is meso. I know you hate it, but I'm sorry. It is meso, so we can just choose to write them as wedges, right? Writing them as dashes would give us the same thing because we just flip the molecule over. Anyway, here we go. So from there, we know that we want to add this nucleophile, which is going to pop open that ring. and it's going to give us this O minus, which is what we were just, which is a little bit pesky, but that's okay, because now we're going to do the hydroboration oxidation, right? And this hydroboration oxidation happens, look, it happens in a base anyway, right? Sodium hydroxide is a base, so it's going to deprotonate it in the end anyway. It doesn't make a difference, right? So we can go through this. We can make our aldehyde.
H2O2, not water.
Oh, yes. Yeah. Missing a 2. Okay. We can go through this. We have this anion now. Okay. And this is the structure that we get out at the end. If you wrote a hydrogen right here, it would not be correct. Well, somebody might get on your case about it. Okay. But that's fine, because adding a hydrogen to a water is the easiest thing in the world. All you have to do is put it in some really just dilute acid, right? Doesn't matter what acid it is, whatever. We just write H3O plus and we're done. Okay. I think in the lectures, I didn't hear him say it, but I imagine by this point he's mentioned the term aqueous workup. So that's what this is called. So this is called an aqueous workup, which is super common at the end of reactions, just so we can get like, we can protonate our alcohols or protonate whatever there is to protonate. Okay. So yeah. A really common final step. It's, you know, this is dilute, right? So it's not going to break any of your functional groups. It's not going to like tear through your molecule. Yeah. Okay. Let's keep moving. Yeah. Yeah, this week's problems have some good synthesis on there. I really like these problems this week, so that is good for us, because we have plenty of these. I actually tried looking at problems relating to alkynes, like finding some of my own. I only found one that was like really good, which is to say that it's like a real pain in the ass, but otherwise, these are really good problems, I think. They involve a good number of steps. So anyway, all right, we have this structure over here, and let's see if anybody notices. There's something that kind of sticks out here. So how do you think we might make this?
With like oxymercuration, demercuration. Yeah,
I'm with you. So yeah, so we might want to start with an alkyne that looks like this, right? That's the right structure, right? I often draw these alkynes with like a bendy bond there, even though...
Isn't there too many carbons?
Oh, did I draw?
Oh, we can add the thing on the end.
1, 2, 3, 4, 5. 2, 3, 4, 5.
The 2 at the left? Aren't those?
Yeah, yeah. So we will have to attach this alkyne. You're right. Yeah. Yeah, maybe we should have started with that, right? Just checking if we can cheese this problem, but we can't because, well, there are 7 carbons to start with, so we'll have to actually attach carbons to carbons, right? But for now, we're just doing that with one way, right? We're just doing that by adding alkynes. So yeah, we'll stick with that. Okay. Anyway, so how do we do this, right? HgSO4, H2SO4. Remember, when there's a triple bond, it just happens in one step. No need to reduce with sodium borohydride. So this is it. Okay. And then let's say we want to break this bond over here. Well, I've already asked you guys this a whole bunch of times, so how about I just tell you, it's SN2 again. Remember, so we do this, And so this happens by SN2. Okay. But let's not kid ourselves. This is not the only way to do this problem, right? This week you'll be learning about organometallics too, and well, some of you have already seen it. So, you know, let's not fool ourselves into thinking that we're not grown-ups and we can't do this multiple ways. Okay. So there's another way to do this problem, in fact, because we have this carbonyl here, right? And yes, we have to make a carbon-carbon bond, but there's a carbonyl, which means that we could have added something at that carbonyl site. Okay. So does anybody see a way to do this problem with organometallics?
So if we like looking at that 5 carbon, I guess, we could have used either a Grignard reagent, just like that whole side of the chain attached to like Mg and a Br, or we could have used a lithium reagent. We could have had the we could use a acid chloride. I forgot what the name of it was, whatever. But if we had that, then that Grignard reagent or that lithium reagent would come in at the bottom, and then the double bond would delocalize to the oxygen, and then that negative charge on the oxygen would come back down, eject the Cl, and then we would have our product.
That is exactly right. Yes. Okay. And so we can often draw it in just like this crazy, like all these arrows at once, right? That just sums up what you said. And there we go. One step. Okay. Usually you have to show how you made this Grignard reagent. So Br, and then, okay, you give it magnesium and you do this in ether. Okay. There you go. That's it. One step. All right. That's if we broke. Let's do different colors. So if we break this bond, then we could do it this way, right? If we break, what's another nice another color? Oh, pink, my favorite. So if we break this bond, we could do this too, okay? And so if we want to do it this way, well, we could do it this way too. Okay, so here we go. This acid chloride has 6 carbons. You can check me on that. Okay. CH3, I don't know. Whatever your favorite thing is. You could use a lithium here if you want this time. Okay. Bam. Okay. There's not just one way to do this problem now. Right. In fact, if you're using these organometallics, you could do this even faster. It's just one step. All right. No need to do the whole SN2 thing. That's a waste of time. Right. So, well, we're getting pretty advanced now. So, you know, there's going to be multiple ways to do it. And yeah.
We have also done this with a sodium amide.
Where?
Not sodium amide, but a one second. Just an amide in general, because like in the organometallic videos, he showed like 2 ways to make ketones, and one was just with like cuprates, and then the other one was with amides.
Okay. Huh. I'm not sure what the way of using an amide to make a ketone would be. Yeah, so you could do this with cuprates too, and I've kind of been like staying away from cuprates. In this case, it doesn't matter if you use a cuprate or an organolithium or a Grignard reagent, they're all the same. If you're doing other reactions, it does matter whether you're using a cuprit or not. I'm not sure what the amide he's talking about is.
It's like a special kind of amide. It's a Weinreb amide.
Oh God, kill me. Yeah. Yeah, so the Weinreb amide it is a special reagent. This one I can't remember the exact details of it, and I have to look it up. I'll try to talk about it on Thursday. Yeah, so the Weinreb amide, I don't know if you can make this specific compound using it. I'd have to double check and look up exactly what it does. Yeah, it's possible that you could use the Weinreb amide to do it. It's the sort of thing. It's not covered in the textbook. It's the sort of thing that like in the past hasn't been covered that much, but like I know last year, for example, there was an exam question which was like, oh, write out the mechanism for using a Weinreb amide to make this product, and like it was worth like some stupid amount of points, right? Like a lot. And people were kind of upset about that one, like pretty rightfully so, if you'd ask me. So, okay, anyway, that is to say, like, the Weinreb amide is like a pretty specific thing, but like they totally might, and in fact, likely will ask about it. Anyway, I don't remember the exact details of it, so I'll need to like look those up and talk about it on Thursday. It's possible that you can make this with the Weinreb amide, but I'm not sure. Is long story short. Okay. Let's keep going. Copy, paste. Okay. So here we go. Oops, I don't want to rotate it. Okay. I just got some really weird window open up. All right. Okay, so we want to make the structure here. And well, there's these two carbonyls. So that might be a little.
Ozonolysis.
Huh?
We could do ozonolysis.
Yeah, so that's an option. So we can do, there's a lot of carbons here, so we're gonna have to figure that out at some point anyway. But let's say we were to have this compound and now this guy over here. Okay, and we were to do ozonolysis. So 1, you add ozone, and then 2, anybody remember?
Sulfur with 2 ethyl groups.
We usually use 2 methyl groups, but I think you
Okay.
can do it with 2 ethyl groups too. I don't think it makes any difference. But anyway, you're totally right. So dimethyl sulfide is good. In this case, because we're just making ketones, you could use hydrogen peroxide too. Okay, so this is reductive. Okay, so if there was something on the end, we would get aldehydes. But because there's nothing on the end, it doesn't matter if we get aldehydes or acids because there's going to be ketones anyway. So we could do hydrogen peroxide here too. Anyway. Okay, let's say we're working with this structure here. And, well, we might get stuck. At least I'm a little stuck. How might we want to go about that? Yeah. Oh, somebody had asked in the chat if there will be a workshop today at 5. No. I actually should have mentioned this. I totally meant to in my email too. The person who runs the other workshops for calendar section, he moved his workshop time to be Thursday. I think it's at Thursday at 7 to 9 p.m. I should totally send out the link for that. Yeah, so that is like the alternate time. So it's not on Sunday afternoons anymore. There's a guy who runs the workshops for Molander section who also does workshops for Sunday. He does them, I think, at 1 to 3. So I guess in a few minutes. I think so. Yeah, I should send out the links for those. Thanks for reminding me, though. Yeah. Okay. Anyway, if we're doing this problem, we get here, I would get pretty stuck. This is a hard thing to make. I can't think of how to make this at any point. Even knowing organic chemistry too, I don't know if we can make this. We're gonna have to think of another option. I'll actually point out what we can do because I don't remember if this is something that's covered in the class, but I know it's a reaction that I've certainly seen before, but I can't remember if he talks about it. So somebody might have to point it out. So if we start with an alkyne, and then okay, we have this triangle here, and then on this side, well, I'm way too lazy, so we have that ring. All right. So if we start with this and we give it KMNO4, and in this case it's cold and dilute again, this is what you wind up making out. You wind up with 2 ketones, right? So it's kind of like you make a double enol, for sort of, right? And then you can tautomerize that into this. All right. So I don't remember if he mentioned that in class, but this is a reaction that we can do. So let's assume that we know that. If he didn't mention it, then let's just assume that we know that's the last step. Okay, and the question is, how do we make this structure here? Okay. So we're going to need to do 2 of these, right? And why don't we even just go ahead and count carbons, because we might be able to get off easy in this question, right? So 1, 2, 3, 4, 5, and 6 on this side, right? We have to start with 6 or less carbons. So why don't we just cut this bond here, and then how do we attach them together?
Did you like the sort of SN2 thing, like the carbon is a negative?
Exactly. Yeah. So we can start with triangles. Okay. So we can start with this, and in this case, it's a little bit tricky to keep track of how many carbons we need, but this is the right amount. Okay. And then we can just do SN2. Okay. But making this thing isn't that hard either. So, well, we know that we can just go backwards, right? And make this pretty easily by also doing SN2, right? We've seen it a whole bunch today, so nothing crazy. Okay. Let's see. One more synthesis. Unless someone has a question.
How would you get like because like you're adding the thing with the at the very bottom, but then like your product has a negative still. Would it normally do that?
No, you'd have to deprotonate again.
Okay.
Yeah, so you're right. Yeah, you'd have to do it again. Let's see. Did I already paste the thing in? Let's get another one. Yeah, here we go. Let's move it up. Okay. And now what are we working with? Well, here is this cyclopropane, right? Okay. And this should always just be like this should always just shout out at you one specific reaction, because there's really just one way to do it. So what reaction is that?
Simmons-Smith.
Yeah, exactly, right? And if you'll remember, Simmons-Smith is CH2I2 and zinc, right? So we're starting with that. Good. Okay. And well, okay, let's count our carbons now, because we've got way too many. So what can we start with? Well, 1, 2, 3, 4, 5. So we could start with 5 carbons down at this end, right? And how can we get this double bond? Like, where could this double bond have come from?
We could use the Lindner's catalyst.
Exactly. Yeah. So H2, Lindlar's catalyst. Perfect. Okay. And now, again, we can count these carbons, right? Well, we already counted them, but.
Wait, Adam, a quick question for using Simmons-Smith. Does it matter if it's a cis double bond or a trans double bond?
So not especially, but the way that this is drawn, well, I don't even, it's not drawn very clear here, but if you're given this problem on like a quiz, for example, it would be likely that they would draw it this way. So for example, they would draw it like this. And so here it does matter if it's a cis or trans double bond, right? So this comes from the cis double bond. And then if we have like, if they're opposite to each other, right? This comes from the trans double bond. So this question doesn't really draw that. I kind of just assumed that they were, that these were like, let's say both wedges, right? They don't have to be. This question doesn't really make it clear, so it doesn't make a difference.
Okay, thank you.
Yeah. Yeah. Anyway, I actually missed a carbon when I was counting the first time, but so here, 1, 2, 3, 4, 5, 6. Okay, so we break our bond right here, and oh my God, it worked once. Okay, don't worry about it. Okay, and I'll see you the unmute click. So this is SN2 again, right? So here we go. Let's start with just an iodide, nice and easy, and drew one too many carbons, but that's it, right? And so this will proceed by SN2. Okay. Cool. There are two problems left. They're both pretty good. Why don't I'll copy and paste them on here, but otherwise, since we're coming up on 1 p.m., I'll well, it is 1 p.m. right now. I will leave them to you to work on them, and it's probably good. We'll probably talk about them on Thursday's workshop anyway, just because it'll be before the quiz and it's extra practice, and that's always good. And okay, why don't I also, let me resend this Google form. So fill that out. Just put your PIN ID, that 8-digit number thing. Fill it out. Put that thing in. Okay. Anyway, so here's problem 2, at least of this week's worksheet, right? So it's synthesize. So that it's there are 2 problems here. So synthesize both of these starting from 6 or fewer compounds, right? Effectively the same as what we were just doing. The last one is to show a mechanism for copy. Here we go. The last one is to show this mechanism, which doesn't come up that often, but well, it very well might, right? So it's to show a mechanism for this. Yeah, we'll talk about both of these problems on Thursday, but the point is there was an extra problem that I found, which I thought was pretty helpful. So if you're looking for a real challenge and you thought all these were too easy, well, here's an extra, I don't know, it's a bonus problem. Okay, so here's a bonus problem. So it's write the mechanism. I'm not going to write out the full problem because if you see the word mechanism, you already know what's coming. So the question is write out the mechanism for this conversion. So we're starting from there and we're going up to here. And if I remember correctly, it was catalyzed in acid, but I forgot to write it down. Okay. So that's going to be fun for you to think about and work on. I'll put up the answers for the problems on the worksheet on the canvas, the workshop canvas. Those will be up there. This one, this problem that I just wrote, well, I'm not going to put the answer up for that one yet. This one you just have to work on. Okay. I'll give you the answer on Thursday. All right. How about I stop sharing my screen?